If a ground rod is used to supplement an underground metal water pipe grounding electrode, it must meet the requirements outlined in the National Electrical Code, specifically NEC 250.56, which mandates a resistance to ground of 25 ohms or less. NEC 250.53 Section 2 provides further clarification stating that where the resistance to ground of the grounding electrode used does not have a resistance to ground of 25 ohms or less, all grounding electrodes within the electrode system shall be connected together, and the combined resistance to ground shall be 25 ohms or less. This means that if you're adding a ground rod to an existing underground metal water pipe grounding electrode, and the combined resistance of both electrodes exceeds 25 ohms, you'll need to take further action. That typically involves installing an additional grounding electrode such as a second ground rod. The purpose of this requirement is to ensure a low impedance path to ground, facilitating the clearing of ground faults and minimizing the risk of electrical shock. A low resistance grounding system helps to quickly trip over current protective devices, such as circuit breakers or fuses, in the event of a ground fault. Now, it's important to understand what constitutes a grounding electrode system. A grounding electrode system comprises all available grounding electrodes that are bonded together to form a single, effective ground. These electrodes can include things like metal underground water pipes, metal frames of buildings, concrete encased electrodes which are often referred to as U for grounds, and of course, ground rods and ground rings. The goal is to create a comprehensive grounding network that provides multiple paths for fault current to flow back to the source. When installing ground rods, there are specific requirements that need to be followed. Firstly, ground rods must be at least 8 feet in length and must be driven into the ground to a depth of at least 8 feet. They should be made of materials that are resistant to corrosion, such as galvanized steel or copper-clad steel. The size of the grounding electrode conductor connecting the ground rod to the service equipment is determined by NEC Table 250.66, and it's based on the size of the service entrance conductors. The grounding electrode conductor must be securely connected to the ground rod using approved methods, such as grounding clamps or exothermic welding. The location of the ground rod is also important. It should be installed where it's accessible for inspection and testing and where it's not likely to be damaged. It should also be located as close as practicable to the service equipment. Now let's talk about the exception to the 25 ohms requirement. NEC 250.53 Section 3 addresses situations where it's impractical to achieve a resistance to ground of 25 ohms or less. This section states that where the electrode system is installed at a location where it is impractical to obtain a resistance to ground of 25 ohms or less, the grounding electrode system shall have a resistance to ground that is as low as practicable. In such cases, the authority having jurisdiction or AHJ has the final say in determining what is considered as low as practicable. The AHJ is the entity responsible for enforcing the electrical code, and they have the authority to interpret the code and make decisions based on the specific circumstances of the installation. In some areas with high soil resistivity, achieving 25 ohms or less may be extremely difficult or even impossible. In these situations, the AHJ may allow for a higher resistance value, but they will typically require additional measures to ensure the safety of the electrical system. These measures might include the use of additional grounding electrodes, such as ground plates or chemical ground rods, or the implementation of ground fault protection equipment. Ground fault protection equipment is designed to detect ground faults and quickly de-energize the circuit, minimizing the risk of electrical shock. It's important to remember that the primary goal of grounding is to provide a safe path for fault current to flow back to the source, regardless of the resistance to ground. A low-resistance grounding system is always preferred, but in situations where it's not achievable, other measures can be taken to ensure safety. When performing a service upgrade, it's essential to carefully evaluate the existing grounding system and determine whether it meets the current code requirements. If the existing grounding system is inadequate, it must be upgraded to comply with the code. This may involve replacing the grounding electrodes, adding additional grounding electrodes, or upgrading the grounding electrode conductor. It's also important to ensure that all grounding connections are tight and corrosion-free. Loose or corroded connections can significantly increase the resistance of the grounding system, reducing its effectiveness. The proper installation and maintenance of a grounding system are crucial for ensuring the safety and reliability of an electrical system. A well-designed and properly installed grounding system can help to prevent electrical shock, minimize the risk of fire, and protect electrical equipment from damage. Always consult with a qualified electrician or electrical engineer when designing or upgrading a grounding system to ensure that it meets all applicable code requirements. Furthermore, it is essential to consider the specific soil conditions at the installation site. Soil resistivity can vary significantly depending on factors such as moisture content, mineral composition, and temperature. High soil resistivity can make it difficult to achieve a low-resistance grounding system. In areas with high soil resistivity, it may be necessary to use specialized grounding techniques, such as chemical ground rods or ground-enhancing compounds. Chemical ground rods are designed to improve the conductivity of the soil around the electrode, reducing the overall resistance to ground. Ground-enhancing compounds are materials that are added to the soil to increase its conductivity. These compounds can be particularly effective in areas with dry or sandy soil. In addition to soil conditions, it is also important to consider the presence of underground utilities. Before driving ground rods, it is essential to contact the local utility companies to locate any buried pipes or cables. Driving a ground rod into an underground utility can be extremely dangerous and can result in serious injury or property damage. Once the location of underground utilities has been determined, ground rods should be installed at a safe distance from these utilities. The National Electrical Code provides specific guidelines for the location of grounding electrodes in relation to underground utilities. It is also important to ensure that the grounding electrode system is properly bonded to other metal components of the building or structure. This bonding helps to create a common ground potential, minimizing the risk of voltage differences between different metal parts. Bonding should be performed in accordance with the requirements of the National Electrical Code. In some cases, it may be necessary to install a separate grounding electrode system for sensitive electronic equipment. This is particularly important in facilities that has computer systems, medical equipment, or other electronic devices that are susceptible to damage from voltage surges or electrical noise. A dedicated grounding electrode system can help to isolate these sensitive devices from the rest of the electrical system, providing them with a clean and stable ground reference. When installing a dedicated grounding electrode system, it is important to ensure that it is properly isolated from the main grounding electrode system. This isolation can be achieved by using isolation transformers or other specialized grounding equipment. It is also important to follow the manufacturer's recommendations for the installation and maintenance of these specialized grounding systems. Regular testing of the grounding electrode system is essential to ensure that it is functioning properly. Ground resistance testing should be performed at least annually or more frequently in areas with corrosive soil conditions. Ground resistance testing involves measuring the resistance between the grounding electrode and remote earth. The results of the ground resistance test can be used to identify potential problems with the grounding system, such as corroded connections or damaged electrodes. If the ground resistance is found to be too high, corrective action should be taken immediately to restore the grounding system to its proper operating condition. In addition to ground resistance testing, it is also important to visually inspect the grounding electrode system on a regular basis. This inspection should include checking for signs of corrosion, damage, or loose connections. Any problems that are identified during the visual inspection should be corrected promptly. The National Electrical Code provides specific requirements for the maintenance and testing of grounding electrode systems. It is important to familiarize yourself with these requirements and to follow them carefully. A properly maintained and tested grounding electrode system is essential for ensuring the safety and reliability of an electrical system. Finally, it is important to remember that the grounding requirements in the National Electrical Code are constantly evolving. It is important to stay up to date on the latest code changes and to ensure that your grounding system complies with the current requirements. You can stay informed about code changes by attending industry conferences, reading trade publications, and consulting with qualified electrical professionals. By following these guidelines, you can ensure that your grounding system provides a safe and effective path for fault current to flow back to the source, protecting people and equipment from electrical hazards. Keep in mind also that the interpretation and enforcement of the National Electrical Code can vary depending on the local jurisdiction. Always consult with the authority having jurisdiction to ensure that your grounding system meets all applicable requirements. The authority having jurisdiction may have additional requirements or interpretations that are not explicitly stated in the National Electrical Code. It is also important to obtain all necessary permits and inspections before installing or modifying a grounding system. Failure to obtain the required permits and inspections can result in fines, delays, and even the shutdown of your electrical system. Working with a qualified electrician or electrical engineer is the best way to ensure that your grounding system complies with all applicable codes and regulations. These professionals have the knowledge and experience to design, install, and maintain grounding systems that meet your specific needs. They can also help you navigate the complex world of electrical codes and regulations. So, to summarize, when supplementing an underground metal water pipe grounding electrode with a ground rod, adhere to NEC 250.56, ensuring the ground rod achieves 25 ohms or less resistance. Per NEC 250.53, Section 2, if the combined resistance exceeds 25 ohms, interconnected electrodes must collectively reach this threshold, often necessitating an additional ground rod. If achieving 25 ohms proves impractical, NEC 250.53, Section 3, allows for the lowest practicable resistance, contingent on the authority having jurisdiction's approval. This multifaceted approach prioritizes safety, ensuring a robust grounding system that effectively mitigates electrical hazards.